Welcome to section 4.3, the mean value theorem. We are using the text Advanced Calculus by Patrick M. Fitzpatrick, and this is Dr. Gilbert, Eyabi. First of all, let's get a remark. Subsection 4.3.1. The mean value theorem, or MVT, is one of the most useful and geometrically attractive results in calculus. Now that we have that out of the way, let's go to subsection 4.3.2. Let's look at a lemma. Let I be the neighborhood of the point x0, and suppose that the function f from I to r, the set of real numbers, is differentiable at x0. If x0 is either a maximizer or a minimizer of the function f, then the first derivative of f at the point x0 is 0. Interesting. So let's look at the picture first. So right here we have the point x0. That's our function y equals f of x. This point is a maximizer because f of x0 is bigger than all the points around this area. At least a local maximizer, if we can put it that way. The first derivative at x0 is 0. x0 here is a minimizer. The first derivative at x0 is 0. Interesting. Where's that leading? Well, we would use that to prove the mean value theorem and many other exciting results in section 4.3. Okay, let's go. By the definition of the derivative, right here, the limit as x approaches x0 from the left of this quantity, f of x minus f of x0 divided by x minus x0, equals the limit as x approaches x0 from the right, and that equals the first derivative at the point x0. So let's look at a couple of cases. Case 1, x0 is a maximizer. Let us prove that f prime at x0 is 0, and then do the same thing for a minimizer. So observe that if x0 is a maximizer, f of x0 is going to be bigger than or equal to f of x for every point x in your entire domain I. So, case 1, let's look at x less than x0. Okay, so we're interested right here. So let's look at x less than x0. Then we'll look at x greater than x0. And then conclude as far as the maximizer is concerned. So if x is less than x0, then x minus x0 is less than 0. So this quantity is less than 0. This quantity is less than or equal to 0 because f of x is a maximum point. As a matter of fact, is the maximum point as far as I is concerned. So negative or 0, negative, so that gives us greater than or equal to 0 for every x in I. Hence, the first derivative of f at the point x0, which is the limit as x approaches x0 from the left, right here, of f of x minus f of x0 divided by x minus x0, is greater than or equal to 0 because this quantity is greater than or equal to 0. Call that inequality 1. On the other hand, let us verify what happens when x is greater than x0. When x is greater than x0, then x minus x0 is going to be bigger than 0. Again, x0 is a maximizer, which means f of x0 is bigger than or equal to f of x for every x in I. So that would mean that f of x minus f of x0 is less than or equal to 0. And the denominator, because x is greater than x0, is greater than 0. And therefore this entire quantity is less than or equal to 0 for every x in I. I.e., the right-hand limit, x approaching x0, the limit of that, f of x minus f of x0, divided by x minus x0 will be less than or equal to 0 because this entire quantity is less than or equal to 0. In other words, f prime at x naught is greater than or equal to 0, and f prime at x naught is less than or equal to 0. Inequality 1, inequality 2. Put those together, and we have that the first derivative of f at x naught equals 0. So that works if x naught is a maximizer. What happens if x naught is a minimizer? Same proof applies with inequalities reversed. And that proves our first lemma in this section. Again, what is our statement of the lemma? If f is a function from I to R, where I is a neighborhood of x naught, and if x naught is either a maximizer or a minimizer, then the first derivative at the point x naught is 0. Okay, please do not forget that. We'll come back to that later. Let's move on. Now, 4.3.3 Rolle's theorem. Suppose that the function f from the closed bounded interval to R is the set of real numbers. Suppose this function is continuous, and the restriction of f to the open interval AB is differentiable, and also f of A equals f of B, then the conclusion is that there is a point x naught in the open interval AB such that the first derivative at the point x naught is 0. Let's list the properties that must be satisfied before the conclusion so that it will be easy to read Rolle's theorem. So here we go. F is a function from the closed bounded interval AB to R. Number 1, f is continuous on the closed bounded interval. Number 2, f is differentiable. This here means differentiable. F is differentiable on the open interval AB. Number 3, f of A equals f of B, and the conclusion is that there exists a point x naught in the open interval AB such that the first derivative at the point x naught is 0. Let's look at some pictures. Look at this first scenario right here. That is A, that is B. F of A must equal f of B. So you can draw as you want, but let's just say you move up and you take a few turns, but you have to come back so that f of A can be equal to f of B. What do you observe? If that is to happen, we create a point that is going to be the maximum, and x naught here is the maximizer. And what did the lemma say again? At the point which is considered the maximizer, the first derivative is going to be equal to 0. Well, what if I decided to go down? Well, I would have created some minimizers, and again, f prime at x naught will be 0. The only other option we have left is, well, a straight line from f of A to f of B. Well, if that is the case, then it's very easy to use your first principle, the definition of derivative, the limit definition, that f prime at x equals 0 for every x in I. As a matter of fact, that's actually the proof of Rolle's theorem in pictures. Proof. F continuous on the closed bounded interval implies that f attains both a minimum value and a maximum value on the closed bounded interval AB by the extreme value theorem, EVT. Now, since f of A equals f of B, number 1, if both the minimum and the maximum values occur at the endpoints, then f is a constant function, right here, in which case the first derivative of f at x equals 0 for every x in AB. Any of those x would be x naught, and we're done. Otherwise, f has either a maximizer or a minimizer at some point x naught. So, it doesn't matter how you draw it, f is going to have a maximizer or a minimizer at some point x naught. And our lemma tells us the first derivative at that maximizer or minimizer would be 0. And therefore, we can conclude that theorem 4.3.3 Rolle's theorem is done. As easy as that. Okay, now let's move on to some more exciting news, the core of what we are looking at today. Theorem 4.3.4, the Mean Value Theorem, MVT. Suppose f, the function from the closed bounded interval AB to the set of real numbers, is continuous, and the restriction of f to the open interval AB is differentiable. Then there is a point, I missed the word is. Yeah, you can forgive me for that. You can insert it. Then there is a point x0 in the open interval AB at which the first derivative at the point x0 equals f of b minus f of a divided by b minus a. Wow, that's interesting. Geometrically, let's see what we're looking at here. So right here, that's the point A, that's the point B, that is our function, y equals f of x. This function is continuous in the closed bounded interval AB. Right here is the point x0, that's the tangent line to the point x0. This point is x0, f of x0. And so we are looking at the difference between f of a and f of b, which is f of b minus f of a. And same thing, we have b minus a. And the mean value theorem claims that there exists a point x0, which is actually this point. The first derivative of this point is going to be the ratio of f of b minus f of a divided by b minus a. In other words, this tangent line and this line that goes from A to B are parallel. They have the same slope. Interesting. Well, let's go ahead and demystify the mean value theorem. Firstly, f is a function from the closed bounded interval AB to the set of real numbers R. Number one, f is continuous on the closed bounded interval. Number two, f is differentiable on the open interval AB. Conclusion: there exists a point x0 in the open interval AB such that the first derivative at the point x0 is f of b minus f of a divided by b minus a. Observe that we have one less condition than we did with Rolle's theorem. We had these first two conditions for Rolle's theorem, and we had a third condition that f of a equals f of b. Now, observe that if f of a equals f of b, then the conclusion of mean values theorem becomes f prime at x0 equals f of b minus f of a divided by b minus a, which equals 0 divided by b minus a, which equals 0, and that is equivalent to Rolle's theorem. So yes, Rolle's theorem is a particular case of the mean value theorem, but these two theorems were proven at different times by different people without plagiarism. Okay, let's move on to the proof of the mean value theorem. Now, let me just warn you well ahead of time. This is not one of those proofs that you're born with. Things are going to just fall from space, and we're going to use them and then show that those things that fall from space work. So don't feel too bad if you didn't figure out from day one or from minute one what some of the things would introduce would be. So let's go ahead and do that. Now, define h to be a function from the closed bounded interval to R. Again, I just defined h. Why did I define h? Well, because I need it. And I decide to define my h as h of x equals f of x minus mx. How could you have known this? From space, I guess. Now, since f is continuous on the closed bounded interval, it would follow that h is also continuous on the closed bounded interval because mx is a polynomial function everywhere continuous. Secondly, since f is differentiable on the open interval AB, h will also be differentiable on the open interval AB. So our h is good to go. It satisfies the two properties necessary for the application of the mean value theorem. Now, this m is just a real number, and I just pull some values for m from a hat. Let m be defined by f of b minus f of a divided by b minus a. A cannot be equal to B, so B minus A is different from 0. That's a real number. And I claim that my M is that number. Why did I choose it? Well, because it's going to work for me. But after this, and after doing this proof a couple of times, you will be able to master this and be able to generate your own proof. Okay? Let's move on. Then H of A, which is just F of A minus MA, becomes B F of A minus A F of B divided by B minus A. Simple algebra, and I'll leave that as a simple exercise for serious students. Just remember that your M is going to be F of B minus F of A divided by B minus A, and just play with this. In the same way, let's look at H of B. H of B would be F of B minus MB or BM, where M is F of B minus F of A divided by B minus A. Again, simple exercise for serious students would arrive at B F of A minus A F of B divided by B minus A. Wait a minute. That's exactly what I got here. Yes. H of A equals H of B. So now we have that H is continuous on the closed bounded interval. H is differentiable on the open interval on the restriction AB. H of A equals H of B. Therefore, we can apply Rolle's theorem. And by Rolle's theorem, there exists a point x0 in the open interval such that the first derivative of H at the point x0 is 0. But what is the first derivative of H? The first derivative of H would simply be f prime of x minus m. You can quickly verify by the definition of derivative that the derivative of mx is just m. So h prime at x equals f prime at x minus m. And if the first derivative equals 0, we are saying here that 0 equals f prime at x0 minus m. And solving for f prime at x0, we have f prime at x0 equals m, and our m is f of b minus f of a divided by b minus a, which we defined. And that concludes the proof, and we're done. That, my friend, is the mean value theorem, one of the most important geometrical results in calculus. Before we conclude all of this, there are a couple of other results we would like to see. So our second lemma for this section, lemma 4.3.5, let I be an open interval and suppose f is a function from I to R, and f is differentiable. Then we claim that f is a constant function if and only if the first derivative is 0 at every point x in I. So, forward direction, suppose f is a constant function, then it is easy to use the definition of the first derivative to prove that f of x equals 0 for every x in I, and I would leave that as a simple exercise for serious students. Now the reverse. Suppose the first derivative of f equals 0 at every x in I. We have to prove that f is a constant function, i.e. f of x equals some c, where c is a real number. Let x naught be a point in I such that c equals f of x naught. X naught is a point, so f of x naught is a point, it's a value. So call it c, and that's a real number. Now let x be an arbitrary point in I. Recall that for every x in I, f prime of x equals 0. So we're heading somewhere. Now I want you to consider the function f from this restriction. X, x0, closed bounded interval. X0 is in I, x is in I, so, and f is continuous on I. So I can talk about the closed bounded interval x, x0, which is a subset of I, to the set of real numbers R. Since f is differentiable, f must be continuous. And f continuous on I means f is continuous on the closed bounded interval x, x0. Also, f is differentiable on I means f would be differentiable on the restriction x naught, which is a subset of I. Therefore, by the mean value theorem, there exists a point z in the open interval x naught such that f prime at z equals f of x naught minus f of x divided by x naught minus x. But since z is in the open interval x naught, which is a subset of I, and f prime at x equals 0 for every x in I, it follows that f prime at z equals 0. But my denominator is not 0. The left-hand side equals 0. That simply means numerator must be 0, i.e. f of x equals f of x naught equals c. Remember, f of x naught was equal to c. And that holds for every x less than x naught. Similarly, we can show that it holds for every x greater than x naught. Of course, f of x naught itself equals c. So, f of x equals c for every x less than x naught. F of x equals c for every x greater than x naught. F of x naught equals c. Therefore, we conclude that for every x in R, f of x equals c, i.e. f is a constant function. Done. Beautiful. And we're going to use that lemma to prove proposition 4.3.6, the identity criterion. Let I be an open interval and let the functions g and h be differentiable. Then these functions differ by constant if and only if their first derivatives coincide at every point x in I. Interesting. Let's do it. Proof. Define f to be the function g minus h. The domains for both g and h are I and I. So f is a function from I to R. Differentiable, therefore f must be differentiable. F of x is g of x minus h of x. So the first derivative by the sum limit theorem and the property of derivatives, the derivative of the sum equals the sum of the derivatives. F prime at x equals g prime at x minus h prime at x. Forward direction. Suppose g and h differ by constant, called the constant alpha. We have to verify that g prime at x equals h prime at x for every x in I. So, if they differ by constant, then the first derivative of f would just be 0 by lemma 4.3.5, in which case we have g prime at x minus h prime at x equals 0. That's the first derivative. And that being equal to 0 simply means g prime at x equals h prime at x for every x in I, and we're done. Reverse. Suppose g prime at x equals h prime at x for every x in I. We have to prove that g minus h is a constant function. Again, the first derivative of f is g prime minus h prime. If g prime equals h prime, then the first derivative equals 0. But f prime at x equals 0 by the lemma we just saw, lemma 4.3.5, means f of x is a constant c, i.e. c equals g of x minus h of x, in which case the difference between g and h is simply a constant c, i.e. g and h differ by a constant. End of proof. Both directions had a simple application of lemma 4.3.5. Let's take a few more exciting results before we get done with this section. Corollary 4.3.7. Strict monotonicity criterion. Let I be an open interval and let f be a function from I to R and f differentiable. Suppose the first derivative is greater than 0 for every x in I, then we claim that f is increasing strictly on I, i.e. if u and v are elements in I with u less than v, we want to prove that f of u is strictly less than f of v. Now, u and v elements in I. Well, why don't we define the function f from the closed bounded interval uv to r? Again, what are the conditions? F is differentiable on I. U and v are elements in I, so we can talk about the closed bounded interval uv. Again, f is differentiable, so it's continuous, so life is good here. So f continues on uv, the closed bounded interval, because differentiability implies continuity. F is differentiable on the open interval uv, the restriction, because f is differentiable on the entire interval I. Remember, uv, the open interval, is a subset of I. So by MVT, there exists a point x0 in the open interval uv such that f prime at x0 equals f of v minus f of u divided by v minus u. But what do we know about u and v? U is strictly less than v, which means u minus v is strictly less than 0, or v minus u is strictly greater than 0. So let's go back. So v minus u is strictly greater than 0. The first derivative of f at the point x0 is strictly greater than 0. That is given. The first derivative at the point x is greater than 0 for every x in I. So this quantity right here is strictly greater than 0. This quantity right here is strictly greater than 0. I'm sorry, but the numerator has to be strictly greater than 0. In other words, f of v is strictly greater than f of u, in which case f is strictly increasing. Or you can say f of u is strictly less than f of v. But whatever the case is, we have just concluded that if f is a function from I to R, I is an open interval, f is differentiable on I, the first derivative of f is greater than 0 for every x in I, then f is strictly increasing. That is called the strict monotonicity criterion. And that brings us to this exciting definition, 4.3.8. A point x0 in the domain of f from D to R is said to be a local maximizer for f, provided that there is some delta greater than 0 such that f of x is less than or equal to f of x0 for every x in D, where the absolute value of x minus x0 is less than delta. Local, that makes sense. Local maximizer, not global maximizer. So similarly, go ahead and define local minimizer. And how would you define a global maximizer or a global minimizer? So right here, if this is our function f, we are not interested in the global maximum. We are interested in a local maximum. So if D were the interval a, b, then x1 right here would be our local maximizer, and f of x1 is going to be our local maximum. Similarly, x0 will be our local minimizer, and f of x0 will be our local minimum. But observe that this point right here is way greater than f of x1. But that doesn't bother us because we are dealing with local maximizers and local minimizers. And that brings us to the last theorem of this section. Theorem 4.3.8. Let I be an open interval containing the point x0, and suppose that the function f from I to R has a second derivative. Suppose that the first derivative at the point x0 is 0. Then the first conclusion, the second derivative at x0, if it is greater than 0, then x0 is a local minimizer of f. And number 2, if the second derivative at x0 is less than 0, then x0 is a local maximizer of f. So this is how we can locate local maximizer and local minimizer. How do we find them? We set the first derivative equals 0 and solve for x0. x0 becomes a candidate for local minimizer or local maximizer. Then we take the second derivative at x0. If it is greater than 0, x0 is local minimizer. If it is less than 0, X0 is a local maximizer. The proof of this is left as a simple exercise for serious students, and you can find it in the text. I will talk some more in class about the exercises I expect you to do from section 4.3. Again, this is Dr. Gilbert Eyabi. Thank you for coming along section 4.3. The next lesson will not be section 4.4. I'm going to take you to chapter 6, and we shall look at the introduction of integration. Riemann Double sums. Thank you and God bless you. Bye-bye.